just getting a very brief, very short introduction to logarithms. Hence why you're gonna learn. You're gonna be introduced to logarithms. Some of you guys have worked with logarithms before in past classes. For this particular course, you don't need to know too much about logarithms. You don't need to know the laws or special properties of logarithms. It's more so, can you take an application problem with logarithms and apply it? Now, not saying that there's not any logs on the SAT or the ACT, so pretty much what we do in this class, it might be a little bit of what you need to know for the SAT or ACT, but you just can't base it off of what we do. So you're going to do some independent stuff for that. But let's talk about logarithms, okay? First off, logarithms are inverses of exponential functions, okay? Logarithms are inverses of exponential functions. So when you have a to the x equals b, log base a of b equals x is the same thing. It's like saying the same thing. So they are equivalent statements. And this is for any b value that's greater than 0. For any b value that's greater than 0. The reason why b has to be greater than 0 is because you cannot take the log of a negative number. Now, did we talk about inverses in this class? A little bit. Go back and look at your inverse notes for me, please. Inverses dealt with the exponent being -1. So like f to the -1 was inverses. When you had an inverse, what did you do to the points? You flipped them, so x became y became x. Mm-hmm. And because of that, when you graphed an inverse function, it was a reflection over that line, y equals x. Okay? So when we talked about exponential functions on Wednesday, I had a graph of 2 to the x power. Okay, 2 to the x power, it had a horizontal asymptote at 0. It crossed through the y-axis at 1, and it increased from left to right. When you look at the equivalent logarithm for that, okay, when you look at the equivalent logarithm, it's basically a reflection over the line y equals x. And so now, instead of it crossing at 0, 1, it's going to cross the x-axis at 1, 0. Because you flip it. It's not going to have a horizontal asymptote. It's now going to have a vertical asymptote. It's still going to increase from left to right. So the pink represents the logarithm of, or the inverse of 2 to the x. Okay, that's what a logarithm is. Okay, it is the inverse. You can solve a log or evaluate a log by writing a logarithm in exponential form. So prime example, if you have a log base 5 of 25 and you're trying to figure out what this value is, you can write it in exponential form, which would be a, your base, raised to the x power equals b. So what would x equal? 2. It'll be 2. So when it says log base 5 of 25, you know that that answer is 2. Okay, so you can solve or evaluate logarithms by writing them in exponential form.
So would there be equal signs there, and you're not being one of 2x and log 2x, like would it just be equal to 0?
You said log base 2 of 2?
It's like whenever you write these, you have it like set equal to something, but like if you have like 2x, it's log 2x.
Log base 2 of x? Yeah. So in this case, these over here are functions. Yeah. And so they would tend to be equal y. Remember on Wednesday we talked about a special exponential function, which was e to the x. It too has an inverse, and it is called the natural logarithm, the ln of x. That's why when you go to press that button in your calculator to get e, you have to press second ln. Okay? They are inverses of each other. This is for all x that are greater than 0. For all x that are greater than 0, the ln of e to the x power is x, and e to the ln of x is equal to x. So it's like they cancel each other out. The ln of e cancels out, and you're just left with the exponent. Same thing, e to the ln cancels out, and you're just left with x. This too is helpful for like SAT and ACT. Ln of e, like I said, cancels out. So if you have something like the ln of e to the 2x, you'll know automatically that ln and e will cancel out, and you're just left with 2x as your answer. Okay? Vice versa, if you have e to the ln of 3, the e and the ln cancels out, and your answer would just be 3. It'll just be 3. Okay? So just a little bit. This is just an introduction. Okay? Some of y'all, like I said, have already learned this. It's more so about can you take an application problem that deals with logs and apply it. Such as this example. So in this example, the magnitude of an earthquake which releases E joules of energy is given by an equation. Okay? If you notice, this particular logarithm equation doesn't have a base. Okay? Logs usually have a base, like log base 2 of whatever, or log base 4. In this case, whenever there's no log written, there is a 10 there, okay? This is called a common logarithm when you have a log that's a base of 10. So a log that has a base of 10, this is called a common logarithm. This is the same type of log that's the actual button on your calculator. So when you press the log button, you're pressing log base 10, okay? That's the one that's on your calculator. So it's asked us to find the magnitude of an earthquake which releases 5.1 times 10 to the 10th power joules of energy. In other words, we're looking for what part of our equation?
Magnitude.
We're looking for magnitude, which means we know what E is. E is
5.1 times 10.
So then to solve this, all we're going to do is we're going to just plug that in. So that's going to be 2 2/3 log 5.1 times 10 to the 10th power, all over 10 to the 4.8 power. And we will type that into our calculator to find out the magnitude of the earthquake. So remember, by pressing the log button, you're automatically doing log with a base of 10. And type it in exactly as we see it. 5.1 times 10 to the 10th power. Remember that caret allows you to go up to the exponent. All that's over 10 caret 4.8. Make sure you go entirely out of the fraction if you are using the fraction feature. And this should be your magnitude. So rounding 3 significant figures, it will be what?
3.94.
3.94. A magnitude of 3.94. We look at B. How much energy is released by a magnitude of 4.3 earthquake, by a 4.3 earthquake? This time we're looking for what variable? We're looking for E, so we're going to plug in 4.3 for M, and then we are going to solve. Now, you're not responsible for knowing how to solve logarithms algebraically. However, if you do remember, you're more than welcome to use that. However, for this class and for this video, we're going to go into graphing. We're going to type in 4.3 into y1, and we're going to type in this entire expression. Oops, what am I doing? Sorry, there should have been an E right here. Now I'm going to type in this entire expression into y2. For E, I'm going to use what variable? I'm going to use x, and then I'm going to look to see where these two curves intersect each other. So, y1, I type in 4.3, and then in y2, I type in the right side. Now, considering I don't know the last thing I did in this calculator, and I'm trying to see 4.3, which is in between 0 and 10, I'm going to go back to my regular window. How do I get there? Zoom 6. And let's see if I see what I need to see. So there's 4.3, and here is the curve. Okay. Some point in time they're going to intersect this. I'm probably going to have to open up pretty wide. And let's just do a little bit of an analyzing here. Okay? At a magnitude of 3.94, we had 5.1 times 10 to the 10th power joules of energy. So that means we probably have to open this up pretty big, if the calculator even allows that. That was just for 3.94. We're trying to get to 4.3. Okay? So let's open this up pretty wide. Let's see if it actually works. Let's do 10 to the 10th power, or 10 times 10 to the 10th power, since we knew that 5 times 10 to the 10th power gave us 3.94 as a magnitude. So when I graph this, there's 4.3, and let's see if our curve intersects. Let's cross our fingers. Hopefully it does. Come on. Go up one more time. Yes. So we're going to go to second trace, option 5, and we're going to click enter 3 times. And apparently I didn't open it up wide enough. When there's no sign change, that basically means that I didn't open up my window large enough. But this is the process that you would go through to basically, again, figure it out. We're using the same features, same properties that we use with exponential functions to solve logarithmic equations. Okay? So our window wasn't wide enough, so we're going to need to open it up some more. Let's do 20 times 10 to the 10th power. We're basically trying to see where our blue line and our red line are going to intersect, and then we need to get that value. So it should intersect at this point, and let's see. So we have second trace, option 5, enter, 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 and sure enough, we do. Okay, now if you notice, this here is in calculator notation. We do not write E on our paper. Okay, that E stands for 10 to a particular power. Okay, standard form scientific notation. So we need to write this number using 3 significant figures. So what would this be?
1.78.
1.78 times 10 to the 11th power. And that would be our answer. So 1.78 times 10 to the 11th power is the amount of energy needed to get a 4.3 earthquake. So anytime you see that E, that means you're talking about scientific notation, also known as standard form, and you want to write it as such. And again, this is how you apply logarithms, basically be able to use logarithms in application problems. This is the bulk of what you would need to know for this class when it comes to logarithms. Pretty much everything else I gave you about the common log, about how to write from one form to the other, that's just extra stuff that would be helpful for like an SAT or ACT.
And you write that unit for joules.
And you would write the units, which would be joules. Good stuff.